So we have done, we were talking about upper process and contact process. About Eba process and contact process. Now, we are talking about Eba process. We said this is Eba process. It's for the manufacture of ammonia. Can you see my screen?
Yes, sir.
Thank you. Eba process is for the manufacture of ammonia, and the raw materials nitrogen and hydrogen. The product is ammonia, and the reaction is exothermic. You have to remember the equation for Eba process. You have to remember the operating conditions. 450 to anything 450 degrees Celsius. Pressure is 100 to 200 atm. Catalyst is finely divided ion catalyst. Now, why do we choose 450 degrees Celsius? Can you read for me?
Okay. The forward reaction is exothermic. A low temperature gives a higher yield but a slower rate. A high temperature gives a lower yield but a faster rate.
Do you understand that? Because the
Mm-hmm.
forward reaction is exothermic, to get more of the product, we need low temperature to move forward, to shift equilibrium to the right, to get a high yield of ammonia, we need low temperature. But if you operate at low temperature, though it will give you what? Higher yield, but what? A slower rate.
Mm.
If you now choose to go for high temperature, it will give you a what? A faster rate, but the yield will be lower.
But lower yield.
Is
Mm.
that okay? So now we now choose a temperature of about 450 degrees Celsius, which is not too high, which is not too low, right? To give
Yes.
a fast rate and a reasonable yield. Is that okay?
Mm.
Now, what about the pressure? Why do we choose 200 to 100 to 200 degrees Celsius? Why the pressure? Yeah, can you read it?
Um. Uh, is that a
From here. From here. Why
Okay.
pressure and why that pressure?
There is a decrease in number of moles of gaseous substances from reactants to products. An increase in pressure, therefore, favors forward reaction, giving a
Come
good
back
yield.
here. Come back here. How many moles of gas here? Two. How
Two,
many moles of gas? Three.
three, four.
So four rather. Thank you. Four. Thank you. So lower high pressure will favor what? Forward reaction. So when pressure is high, a high yield of ammonia is obtained. Apart from that, when pressure is high, a faster rate is also obtained. So the pressure that is high now give us a dual purpose, favors forward reaction, also give a faster rate of reaction. Do you agree to that?
Yes,
So
sir.
that's why we choose high pressure. Now, catalyst. Why do we use catalyst? Go on.
The catalyst increases rate by lowering activation energy, thus reducing the time taken for the reaction to reach equilibrium.
Go on.
And finally, in finely divided form,
What
the
that means
cat-
that in powder form. Finally, added me powder. Like powder. Is that okay? Go on.
the catalyst is more efficient. The catalyst, however, has no effect on the yield of ammonia.
Do you
The
understand
yield
that
is
now?
15 to 20.
Yield of ammonia is what? Determined by temperature, concentration, and pressure. Is that okay? Catalyst does
Mm.
not affect yield of ammonia. Is that okay? Of any reversible reaction. Now, look at this diagram. I want to explain diagram to you. Please pay attention. This is where the reaction occur converter. Now, the temperature here is about 450 degrees Celsius. But you are taking nitrogen from the air and you are adding hydrogen. The temperature is about room temperature. You cannot just change from room temperature to 450. It's not done anywhere in the world. You know water dispenser.
Mm. Yes.
Do you know the principle by which it's cool and hot? There are two compartments inside the water condenser. Two compartments. A part that cools, a part that heats up. The heat lost by water is gained by the other water. You can so there's no heating anywhere. It's like you have
Mm-hmm.
two compartments now. This same thing here. Now let me clean this one now. This is what happened here. This one goes like this. That's how it really look like. Then this one come like this. Can you see? So it's
Mm.
like there are two. Or let me make it up down. Let me make sense. Up down, up down, up down, up down, up down, up down. Then now this one now, let me make it black. Up, down, up, down, up, down, up, down, up, down, up, down. Can you see now? The two of them
Mm,
are beside each other. There are two pipes. Now,
mm,
the red guy is the one bringing in nitrogen and hydrogen into the converter. Do you get it now? The
mm-hmm,
red guy, that red pipe, is the one bringing what? Nitrogen and hydrogen to the converter, right?
mm,
As it's going, is what? Is getting hot. How is it getting hot? This one, this pipe, look at this pipe. Oh, this pipe, this one, go this way. After ammonia has been produced from ammonia, we produce ammonia, follow here, ammonia. Ammonia. The ammonia is very, very hot. We want
mm,
to cool it down. Ammonia will then enter the black pipe. Can you see that? Enter the black pipe. Are you there?
mm.
Is losing heat to the nitrogen that is coming in.
Okay.
Do you get English?
Yes,
This
sir.
is ammonia. Look, ammonia. Oh, this is look at ammonia. Ammonia is losing heat. Losing heat. Then come out of here. This is this is hydrogen and hydrogen, hydrogen and nitrogen. They are gaining heat, gaining heat, gaining heat, gaining heat, and go. It's like you place hot and cold things. You want that hot thing to become cold. You want this
Mm,
cold thing to become hot. So you now place them side by side. The hot guy loses heat, the cold guy gains heat. Is that okay? So it is not lost, it's not gained. Do you get it? At the end of the day, it's being efficient. Should I say that again?
mm-hmm.
It's like the waste of one material is the raw material for the other one. The waste of a process is the raw material for another process. You know that will make you make enough gain. Do you get the point now? The waste, you
Mm,
are doing two processes in your industry. The waste on one process is the raw material for the other process. Imagine that makes it cool for you. Do you get the point now? Maybe you
mm,
plant corn, on your maize. You are a farmer, you plant corn. You harvested enough corn. You now remove the corn from the cob. You now use the cup to make maybe poultry feed. You didn't throw the cup away. Can you imagine? You remove the
mm,
corn from the cup. You now use the cup to make poultry feed. That's how will happen. So same thing here. The ammonia that is created is ammonia that is coming from look at ammonia. Ammonia produced coming from look at ammonia. Ammonia is very hot. You want to collect liquid ammonia here. Liquid ammonia. Look at it.
mm,
That's ammonia liquid. To get you can't just take hot ammonia straight here. It won't work. It's too hot. You can't come straight directly like that. We now say, okay, you know what?
mm,
This ammonia coming out, you come here, come here. Come and lose it to the nitrogen coming in. Look at ammonia, 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 ammonia. It's now cool a little. But on the other way, look at nitrogen coming in, nitrogen is gaining from ammonia. Do you agree? They don't
mm-hmm.
meet, but the pipes are beside each other. Do you get now? So
Yes.
as nitrogen is going in, is gaining heat. As ammonia is coming out, is losing it. So at the end of the day, heat lost by ammonia is heat gained by what? By nitrogen. At the end of the day, you don't have to heat them. You don't have to heat them again. Do you get the point now? It pays
Mm,
you. So what happened is, let's start again now. Nitrogen and hydrogen enter here. Nitrogen and hydrogen enter here. By the time they come and they are already hot. Do you agree to that?
yes.
How do they get they gain heat from the ammonia that is coming out. When nitrogen now gets here, of course, the hydrogen will occur here. This hydrogen will occur N2 plus 3H. That's converter to give what? True ammonia. All of them come out now, both ammonia, nitrogen, and hydrogen. Not all nitrogen. Remember, we said the yield is about what? 15 to 20%. That means only about 15% of the nitrogen were converted to ammonia. Do you agree to that? The remaining one
Mm,
remain as what? As nitrogen and hydrogen. Do you get? It's a
mm,
reversible reaction. The yield is very low. Is that okay? No. If you want the yield to be very high, you have to go for very low temperature. And if you do that, your rate will be too slow. Do you get the point now? We don't want that.
yes.
Yield is not very high. If you want your yield to be very high, you have to go for very low temperature. You're going to get large amount of money, but at a very slow rate. In that sense, you can, if you use very low temperature, you listen to me. Now we use 450 degrees Celsius. The yield about 15 to 20%. If you go for 300 degrees Celsius, the yield may increase to like maybe 25, 4 to 30%. Can you see now? Yield will be increasing. Go
Mm,
for 200 degrees Celsius, it may become to 36, 38%. Can you see that? It's increasing. Go for 100
mm,
degrees Celsius. You may increase to maybe 40% to 45. Then again, go for that again. You say, okay, let me go for another one. Let me go for that again. Go for 50 degrees Celsius. May get up to 60% yield. But if you get 60% yield, it takes a long day. At the end of the day, it won't pay you. But okay, now if you want to get 60% yield, you now spend Instead of you spending 1 month, you now spend 5 months. I choose to. You have to pay your workers for 5 months. It don't pay you. It's
Mm.
not economical. Do you get? So the yield
Yeah.
you can't say because you want to go for high yield, not go for slow rate. It doesn't pay you. Go for a yield that is not too low, then go for a rate that's not too high. Try to balance the two of them. Do you get? So the
Mm.
effect is that if you increase temperature high, the yield, the rate of conversion, the conversion rate, the conversion amount may increase, but the rate will be very, very slow. Is that okay? Do you get the point
Mm.
now? Good.
Yes.
So by the time you get let me make it black. Ammonia coming out, ammonia coming out, ammonia coming out. Ammonia lost it to the incoming nitrogen and hydrogen. Do you have the ammonia? It lost it to them. So the ammonia coming out, is now cooled. Can you see now cooled?
Mm.
Ammonia that come out of that converter is hot. The one that come out of the heat can you call it, what do you call it? What's the name what's the name?
Heat exchanger.
Thank you. The heat lost by one is gained by heat is being exchanged. That's what we are
Mm-hmm.
doing here. Heat is lost by hot ammonia, is gained by nitrogen and hydrogen. Is that okay? Ammonia coming out
Yes.
is now cool. Cool ammonia coming out coming in now. We now apply very low temperature here and high pressure. Ammonia will liquefy. We turn to liquid. Now call it ammonia. What does this mean? Look at it now. Yeah, look at the equation so that I can get it ready. Look at the equation.
Mm.
What are you when you remove ammonia from what are you doing? You are decreasing the concentration of ammonia. You are removing ammonia. What happened? This will react and go back to ammonia again. Do you agree? Remove the ammonia again.
Yes.
You are decreasing
Mm-hmm.
concentration of ammonia in the mixture. Then the guy will produce ammonia again. Now, this is the guy, nitrogen, hydrogen, ammonia. If you apply, if the pressure is too high, all of them will turn to liquid. But of all the three of them, ammonia will turn to liquid first. Why? Because ammonia has hydrogen bond between its molecule, which is very strong. Do you get? So the hydrogen bond
Yes.
in ammonia makes it liquefy first. But nitrogen and hydrogen, they are close to ideal behavior. They will not liquefy on time. Do you get the point now? Ammonia is the one that deviates most from ideal behavior. It liquefies first because of stronger intermolecular hydrogen bonding. After you now remove ammonia, excuse me, after you remove ammonia, what happened? You recycle nitrogen and hydrogen, and the whole process begins all over again. Can you now see again now?
Mm.
Do you get the process? I think you now
I'm
go and
not.
join again.
I'm not
Yeah.
getting the part where you talked about the hydrogen bonds and ideal. Can you explain that one again?
Say that again.
When you talked about which one liquefies first.
Okay. If you apply high pressure, what happens to gases? Will they deviate from ideal behavior or they will conform? They will deviate, they turn to liquid. Because of now, when you look at it now, just pay attention.
Okay.
The stronger the intermolecular forces between a gas, the easier it liquefies. That's my point. If the
Mm-hmm.
force between the molecules are very strong, the guy turns to liquid on time. Do you get that? Another one? Do you get? Therefore, now pay attention. Steam, chlorine, hydrogen. Which one deviate most from ideal behavior and why? Hello?
The hydrogen.
No, it's steam that deviate most. Let me show you. Let me show you my set of material. Let me quickly show you. I maybe I've not gotten time to read it. Don't worry. Let me quickly show you. No. Yes, no, yeah. Let me show you my. I want to show you something. You understand? Don't worry. Just relax. Set of
Okay.
matter. Set of matter. Fine. Yeah. I want to see which gas normally deviate from ideal behavior. The stronger the intermolecular forces, the easier they deviate from kinetic theory, the easier they deviate faster. If the forces are very strong, kinetic theory say, why do we say that? Come and see. It says there are no intermolecular forces between the gas molecules. We said there are no force between them. So the one that have the
Mm.
greatest intermolecular force is the one that is very far from ideal behavior. When you are far from it, you are turning to a liquid or turning to a solid. Do you get? Come and see.
Mm.
Come and see here. Yeah, look at this. Look at the three of them. Yeah, hydrogen, chlorine, ammonia. Who is very close to ideal behavior? Look at the ABC. Who is closer to that? Who is closer to ideal behavior?
B.
Ideal behavior is a straight line but parallel. A is also a straight line, not just parallel. A is the
Mm,
closest, not B.
okay.
Ideal gas says the product of pressure times volume against pressure is always a straight line parallel to the y-axis, to the x-axis. Is that okay? A is
Mm,
also a straight line. Oh, no, it's not parallel. A is the closest. Do you agree? Followed
mm-hmm.
by B. C is the farthest from ideal behavior. We say A could be what? What could A be? Look at what could A be? Hydrogen. Why? Why do we say A is hydrogen? A could be hydrogen. Okay, good, good. Can you read this?
As the strength of intermolecular forces increase, deviation from ideal gas behavior also increases.
Do you get the point? So the one that deviates most is ammonia. Why? It has hydrogen bonding. The one that is very close to ideal behavior is not there, but very close to it is hydrogen. Why? It has weakest intermolecular. It only has IDID. It has the weakest intermolecular forces. So it's very close to ideal behavior. Do you get the point now?
Mm,
So my point is this. When you apply high pressure, gas liquefy. The gas that liquefy first is the one that have the strongest intermolecular force.
okay.
When you apply high pressure and low temperature, come and see. When you apply high pressure and low temperature, condition when they approach ideal behavior when temperature is high, pressure is low. And now say, come and see. I say at low pressure and high temperature. How do I say? Come and see. You say I'm going to apply low pressure. I mean, at low, at high pressure and low temperature, high pressure, low temperature, high pressure, low temperature. Ammonia, because it's the one that is very far from ideal gas behavior, it turns to liquid first. If the pressure is too high, all of them will turn to liquid. Oh. You have to
Mm-hmm.
apply a pressure that can turn ammonia to liquid. But that pressure is not sufficient enough to turn nitrogen and hydrogen to liquid. So it has to be practicalized. They will know the temperature, they will know the pressure at which ammonia liquefies. We know the pressure at which ammonia liquefies. Is that okay? That
Mm-hmm.
pressure is not sufficient to liquefy nitrogen and hydrogen because they are very close to ideal behavior. They have look at nitrogen. This is ammonia. Look at it. This is ammonia. Oh, ammonia. Can you see? See how strong the intermolecular forces are.
Mm,
Ammonia, intermolecular forces, ammonia. Can you see now? So that means the guy is the force is strong enough for it turns to a liquid. But look at chlorine. Chlorine. Look at chlorine. Chlorine is not strong enough. Chlorine. Chlorine. But we look at hydrogen. Hydrogen. Can you see now? Forces are very weak. Hydrogen. Hydrogen. These two they both have ID. But this guy has greater number of electrons. Am I right? So it can turn to
mm,
liquid, it can have what? Smaller number of electrons. Smaller number of electrons. This one has what? Hydrogen bonding. Hydrogen bonding. Is how can you see that? That's how it goes. So which
mm.
of these I deviate most from ideal gas behavior? Ammonia, chlorine, or hydrogen?
Ammonia.
Thank you. Therefore, which of them under similar condition, if low high pressure is applied, which of them turns to liquid first?
The one with the smaller electrons. The hydrogen.
No, I'm saying here that the one that had the strongest intermolecular force deviate most from ideal gas behavior is the one that will turn liquid first before other gases. Oh, yeah, come and read this place. I'm trying to connect the two together. I can understand. Don't worry, you get it now. Let me go and see. Hey, the day I wrote one story like that. Where I wrote, where I extrapolate, in the place where Charles Law. I'll show you now. Aha. Okay, good. Yeah. Can you read this?
Absolute zero is the lowest possible temperature where heat energy is absent in a substance. It is the temperature at which the
Everybody, sorry.
most.
Come here.
In practice, real gases do not attain this temperature. Most gases liquefy and solidify before this temperature and would have ceased to be gases.
You get it? Would have turned to liquid. So the one that turned to liquid first, you know that I don't want to be a gas. I don't want to be a digger. I want to become somebody else. Leave me. Don't trouble me. So how do we know the one that turned to liquid first? I'm not telling you the principle is this. The principle is this. It's stronger. They just know that. The principle is this. The stronger the intermolecular forces, are you there? The
Yeah.
greater the deviation from ideal gas postulate, and the easier such gases liquefy, turn to liquid. Is that okay?
Mm-hmm.
Gases that deviate from kinetic theory, they liquefy earlier than those that do not deviate from it. Is that okay? The
Yeah.
stronger the IMF is in intermolecular forces, the greater the deviation from ideal gas postulate, and the easier such gases what liquefied. Do you get the point now? So if you apply the same pressure for hydrogen and nitrogen and chlorine, because ammonia is the one that deviate most, it turns to liquid first. Who will turn to liquid last year? Who turns to liquid last year?
The hydrogen.
Hydrogen. Now to prove now, I need to be sure you understand because this is science. Now look at it.
Mm.
Yeah. Suppose we have solid hydrogen, we have liquid hydrogen. Are you there? We
Yes.
have gaseous hydrogen. So now we also have solid ammonia, liquid. We are going to check the on the board now. Liquid ammonia, gaseous ammonia. What do we call temperature at which a solid become liquid? What do we call that temperature?
Which temperature?
The temperature at which a solid turns to liquid. What do we call that temperature?
The
The temperature at which a solid turns to liquid. What do we call that temperature? Melting
freezing
point. Is that correct?
melting point is.
Good. Let's go and check the melting point of hydrogen. Is the temperature at which solid hydrogen become liquid hydrogen. Do you agree to that?
Mm-hmm.
It's also the temperature at which liquid hydrogen becomes solid hydrogen. Do you agree?
Mm-hmm.
Then what's where by the boiling point of hydrogen? The temperature at which liquid what hydrogen becomes gaseous hydrogen, right?
Mm-hmm.
Is it also the temperature at which gaseous hydrogen turns to liquid hydrogen? Is it the same temperature? Yes. Let's go and
Yes.
check it online. Let's go and check. Let's get boiling point of hydrogen. You get the point now. Boiling point of hydrogen minus 252.9 minus 252.9 degrees Celsius. That's the temperature. Let's check the boiling point of what? Of ammonia. You see that ammonia will be easier to, you see now, ammonia. Hmm, Let me write it out. Of ammonia. Minus 33. Can you see now? Let's just minus 33.34. Let's just minus 34. Minus, can you see now? Yeah, look at it. Both of you, so you have gaseous hydrogen. Are you paying attention, Tamunda? You
Yes,
also
sir.
have gaseous ammonia. You are cooling them. When they turn to which one turn to liquid first? Look at the temperature. You are cooling them from 25 degrees Celsius to 24, 23,
Yeah.
22, 21, 20, 0, -1. Which one turn to liquid first? Ammonia. At very fast, look at the difference between them. It's not to liquid
Mm.
first than hydrogen. Because ammonia deviates more from kinetic theory. You guys say that. Look, all this possibility that hydrogen gas will remain light gas. Me, I don't game for that. So I don't the liquid at any time. I don't want that ideal behavior. I don't want it.
Mm.
Ammonia has stronger intermolecular forces. So it turns to liquid first before hydrogen does. Under
Okay.
similar condition. Now, to put my point, let's go and do chlorine. You see that chlorine will be intermediate between both of them. Chlorine, gas, chlorine, chlorine solid, sorry. Chlorine liquid, am I right?
Mm-hmm.
Then chlorine gas. Yeah, let's go and see chlorine. Boiling point of chlorine. It should be lower than ammonia, but not as low as hydrogen. Minus 34, minus 34. Oh, minus 34. Let's see, minus 34.6. Let's see, minus 34.6. Let's write the real one of ammonia. Of ammonia. Minus 33.3. Minus 33.3. Can you see now? 33. Can you see now? So who turns
Yes.
to liquid first of all of them? Ammonia, later chlorine, much later hydrogen. Do you get? Why
Yes.
is that so? Because ammonia is the one that deviates most from kinetic theory. It has the strongest intermolecular forces. Is that okay? So
Mm.
when you come here now, so when you bring all the three here now, let's go now. Bring all the three here now. Who comes here? Hot, ammonia, and then all of them go here. They are now cool now. Three of them will enter here. We apply a pressure. Before you know, let's find for nitrogen so that I can know them. Suppose we just apply low temperature. Suppose we apply low temperature for all of them, nitrogen. We keep the same pressure, or we use other similar, we use the same pressure. That is what minus 190 what? 195.8. Let's do, since it's nitrogen we need 195.8. Nitrogen solid, nitrogen liquid, 195.8. Can you see now?
Yes.
Ammonia minus ammonia liquefied before all of them. Faith, the difference is just too much. Do you get?
Mm.
Minus 195.8 degrees Celsius. Who liquefy first? Ammonia, followed by nitrogen. So we're going to, let's say we are changing temperature here. We just, you know what we're going to do? And listen to me. We can cool, if you cool the mixture of gases to minus 50 degrees Celsius. Who will turn to liquid among them? Only ammonia, right?
Mm.
What happened to that? They will remain gases. They won't liquefy. So they will still remain in the equilibrium. So when ammonia turn to liquid, we remove it. The ammonia will not pass. It come out of it. Or that will not be
Mm-hmm.
recycled. Do you get the point now? Cool it to
Yes.
minus 50 degrees Celsius. If you don't change, so what happens if they answer that here, what can make ammonia to come liquid? Is either you use low temperature or high pressure. Those things that will make a gas not to behave like an ideal gas again. Those things that
Mm-hmm.
will make a gas, look at it. Those things that will make a gas not to behave like what ideal gas again. Come and see. We say at low temperatures and high pressure, gases tend to deviate from a big. Why? Why? Because they liquefy, they turn to liquid at that temperature, they turn to liquid. You say, I'm no more gas, I'm not liquid, I'm not like gas. Is it something that's not a gas that you be saying is it something that's not a gas that you be saying you should obey ideal gas theory? It's no longer a gas, you cannot obey. It has to liquid entirely. So for the three of them, Mr. Ammonia has the strongest intermolecular force. Mr. Ammonia, when low temperature is applied and high pressure, ammonia turns to liquid first before that does. Is that okay? So ammonia
Mm-hmm.
will condense and come out of the mixture. Then you now recycle this guy, recycle hydrogen and nitrogen. Do you get now? Then the whole process will start all
Yes.
over again. Do you get the point now?
Yes, sir.
So the heat exchanger help us to exchange heat between hot ammonia and the cold nitrogen and hydrogen, we are just coming in, right? It heats
Mm-hmm.
them up to increase the rate of reaction. Is that okay? They get
Mm.
here, ammonia is produced here. We now take the hot ammonia back to the heat exchanger to release it to them. Cold ammonia comes out of here. We now liquefy it here. Ammonia comes out as liquid. Then we recycle nitrogen. So the whole thing be just like that all over again. The actual reaction, look at it now. The actual reaction occurs where? This is the converter. In the converter, I label it. Yeah. This is the converter. This is heat exchanger. And this is condenser. Condenser turns liquid ammonia to what? Gaseous ammonia to liquid ammonia. You know that now, right?
Yes.
Condenser. It turns
Mm-hmm.
gaseous substance to liquid substance. Remember, in
Good.
this we are taught in the IGCS now. Look at condenser. This one. We are doing
Mm-hmm.
distillation. Yes, it now. We are doing distillation. You do this, right?
Yes.
Uh-huh. Water inlet,
Mm-hmm.
water outlet. Am I right? Uh-huh.
Yes.
Outlet. Yeah, can you now see?
Mm,
So condenser is to turn vapor to liquid. That was a condenser. Same thing with this guy. This guy is a condenser. It turns gaseous ammonia to liquid ammonia, and the whole thing becomes like that. Is that okay? That
mm,
equals. I think that makes sense.
A lot, and you're like, okay, do you have a private tuition? Don't you have? Do you have? And yes, Agile Tech do have a private tuition. So by my right, you can see that we have for the EdXL and Cambridge IGCSE. And yes, we do have for all subjects. Okay, all subjects. Okay, the popular ones that's always been in demand is mathematics, English language as a second language. Okay, we have physics, we have biology, we have chemistry, and we have um, you know the flagship, which is ICT, just here and there. We also have business studies. So if you're interested for a private tuition, um, I think all you have to do is send an email to the sales team at agiletech@gmail.com, and they would reply to you, talk about your time zone, talk about, and the fee is really quite affordable. Really, it's really quite affordable. It's when you look at it across um, other tutoring service, I think this is the one that's quite affordable, and you get the very best of service. We also have for the E levels as well, um, and also for the EdXL. So we have for the Cambridge E levels and EdXL E levels. Okay, and we have also across the subject mathematics, which is usually the hot cake when it comes to E level, mathematics and chemistry, and then biology. These are usually one of the ones we have in demand always, all the time. Even physics, for E level. So all you have to do, if you're watching this right now and you are interested for a private tuition, then you can do yourself a solid, okay, and send an email to the sales team at agile@gmail.com, and they'll reply to you. And the good news about this is what I've discussed with the sales team is we've tried as much as possible to see how we can subsidize the amount according to countries, so it doesn't really look very, very heavy. Okay, so this is really important. Yes, we do charge in pounds, but again, we try to be as much as possible considerate to your countries, and we don't just skyrocket the price. No, because at the end of the day, we know how it feels, and we really want you to actually get the best of service, and again, be able to afford it from the comfort of your home. So again, Agile Tech private tuition is currently ongoing. You can enroll yourself for the IGCSE, and then for the E levels. Again, for the IGCSEs, these are the subjects, and for the E levels, these are also the subjects. So, again, what are you waiting for? Just send an email to the system. If you're an IGCSE student preparing for IGCSE, if you're watching this in 2024, 5, watching this in 2026, watching this in 2027, we're currently ongoing, and this is actually a good time for you to actually explore, and then get it tailored to your own needs. So trust me, you don't want to miss out.
Now, number two, contact process. Can you read, please? No, let me just read for you. There are five
contact
stages to see.
process.
First, burn sulfur in oxygen to get sulfur dioxide.
Mm-hmm.
So this is the contact stage. This one is one couple of gone. Though this is the process for producing sulfuric acid. Before that, this is in GCSE. You burn sulfur in here to get SO2.
Mm,
SO2 is now burnt in here to get SO3. This is the contact stage here, this stage. Then SO3 is not dissolved directly in water. The reaction is too exothermic. Sometimes it goes out of control. We dissolve SO3 in concentrated sulfuric acid to form oleum. Oleum is now diluted with appropriate volume of water to form concentrated sulfuric acid. SO3 is not dissolved in water. You could have dissolved SO3 in water, you could have done SO3 plus water to give what? H2SO4 to work now. But this reaction is too exothermic. You may not be able to control it. Sometimes it goes out of control. To avoid that trouble, We first
Mm-hmm.
absorb the SO3 produced in concentrated sulfuric acid to form oleum. Are you there? Oleum
Mm-hmm.
is now dissolved in water to form sulfuric acid. The contact stage is 2SO2 plus O2 to give 2SO3. The full reaction is what is exothermic and is more exothermic than Haber process. Haber process is minus 92 kilojoule per mole. This one is minus 197, more than times 2. So it's highly exothermic. Is that okay? Temperature
Yes.
again, 450 degrees Celsius, pressure 2 atm, then catalyst V205. Let's talk about it now. Yeah, let's go. Why do you use 2 atm pressure? Because you know what? This is what happened for contact
Mm-hmm.
process. When pressure was low, the yield was already high.
Mm-hmm.
So let's now you use 2 atm. Look at this contact process. Let's see it. Contact stage, contact process. When you use when you use 2 atm, the yield for me was like the other yield is about, I think it's around 96%. It's very high, more than upper percent. It was maybe 96, 94% or 96%. When you make it 4 atm, become 96.3%. 10 atm, it increased also 97%. 20 atm, 97.4%. People now say, is it worth it to increase it? No. The money you are going to spend to convert this to this,
Mm-hmm.
friends say it's not worth it. Do you get the point now?
Yes.
To operate a reactor at 2 atm or to operate at 20 atm, the difference in the capital is huge.
Mm.
But though there's an increase, there's an increase here, right?
Mm-hmm.
The increase is not worth it. Do you get the point now? So we
Mm-hmm.
use low pressure because the yield of reaction was already high, even at low pressure. Though when we increase the pressure, yield also increase. But the increment is not what the difference in the money. The capital requirement of this change from 2 atm to 20 atm. The capital investment is much more than the yield, the difference in yield. It's not worth it. Do you get the point? So
Mm.
you can't just use our 2 atm. So there's no point using 2 atm is used because of the operating at 2 at high pressure is what is very costly and cannot account for the difference in yield. Do you get the point now?
Mm-hmm.
There's an increase in yield, but it's not worth it. So
Yeah.
2 atm is used. Why? Because operating at 2 atm high pressure is very, very high. Is that okay? Now
Mm-hmm.
go on. What are the raw materials for contact stage? SO2. Where do you get this guy from?
Where do we get?
This
Uh,
guy. Where do you get it from? From air. So
mm-hmm.
oxygen is used as source of air. Air is used as source of oxygen. Do you get the point now? Air is
Mm-hmm.
used as source of oxygen. Now we are read this now. Read.
The, the air must be pure because the catalyst is poisoned if impurities are present.
Do you get that now? So you can't use polluted air. You can't use air that contains dust. It won't work. It must be
Mm-hmm.
pure. If not, your catalyst will not work again. And if it
Okay.
doesn't work again, you have to heat it to higher temperature because it can work. Because it was the catalyst that helped you lower the activation energy requirement. Is that okay? Please go on.
Yes.
Go on.
Large volume of air is used in the contact stage to
What, oh,
to
yeah, what do you think I wrote
to
there?
drive
Thank you. To
equilibration
drive the equilibrium position to the right, thereby increasing. Come
to
back
the
to it.
right.
Thank you. Look at the equation. This is the contact stage. Use large volume of air so that you can get high concentration of oxygen. What will happen? Equilibrium will go to the right. Am I right? Air is available in the atmosphere now.
Mm-hmm.
So why are you managing air? Use large volume. I know you that you are adding what?
Mm-hmm.
Excess O to the going to the right. You're going to get large amount of what of your product. Do you get? So large
Mm-hmm.
volume of air
Yes.
is used to drive equilibrium position to the right, thereby increasing what yield. Go on.
Mm-hmm. The reaction is highly exothermic, hence catalyst must be cooled period periodically so that the optimum temperature is not exceeded, which can lead to a lower yield.
Now the reaction, this is the catalyst is like powder. Look at this catalyst. This is where the reaction is occurring.
Mm-hmm.
We are operating at what temperature? 450 degrees Celsius. As they are reacting, the reaction is very extreme, much more than 2 times for ABA process, more than 2 times. This thing has 450, before you go to 500, get to this 100. But then you get to this 100, what happened to rate of reaction? It will increase. What happened to the yield? The yield will drop.
Mm.
To avoid that, you must be cooling the catalyst once a while. If not, it gets hotter than expected. This will affect your yield because the fall reaction is what? Is exothermic. Do you get the point? So cool the
Mm-hmm.
catalyst once a while. The catalyst will become hotter and hotter. And when it goes hotter, of course, temperature is increasing, therefore rate yield will low. Is that okay? Do you get the point?
Mm-hmm.
Good. So
Yes.
catalyst will be cool so that the optimum temperature of what? Of 450 degrees Celsius is not what? Is not exceeded. If not so, the yield become lower. Do you agree to that?
Mm.
Good. Thank you. So you need to know these 5 equations. You may also write all of them from S to
Okay.
S2, SO to SO3, SO3 to helium to sulfuric acid. You must know that it is exothermic. You must know the formula of the catalyst V2O5 and the name of the catalyst for NO5 oxide. Then the temperature of 50 degrees, just like other process. Then the pressure is 2 atm. Why do we use low pressure? Operation at high temperature is too costly. Is that okay? It's too costly. It's not worth it. Not worth it. Is that okay?
It's not
Why
worth,
must
yeah.
you use,
Mm.
say that again? I'm listening.
I was agreeing about the low pressure.
The pressure already give us high yield. So why going for high pressure? It's not.
Mm-hmm.
Though, if you increase pressure, yield will increase, but the increment is not worth it. Do you get it? It's not
Mm-hmm.
worth it. It's like you are working with a company for 2 days and they give you $10,000 per month. 2 days. You now say, hey, Tamuda, can you make it 3 days? We give you 11,000. You tell them you don't want. Am I right? Because
Yes.
if I work for 2 days and you're giving 10,000, but I work for 3 days, you give me 15,000. Do you agree? You now say that you are
Mm-hmm.
working, you only come 2 days a week. You are a doctor. You come 2 days as a consultant to our hospital. Just 2 days, you give $20,000. For you now say, can you make it 3 days? You know how much we pay? Now say, we pay 22,000. You say, because of one day, they now give just 2,000. You say you don't want. Am I right?
Mm-hmm.
It's not worth it.
Yes.
So they increase the bed. The increment is not worth it. Do you get that? Will happen? We increase pressure,
Mm-hmm.
yield will increase, but it's not worth it. The cost of operating at high pressure is too high. And again, safety reasons. Oh, I didn't add that. We noted that. Why do we use ATM in contact process? Number one, cost. Number two, safety reason. Do you get? If pressure
Mm-hmm.
is very high, there's a risk of explosion. Oh, you know that. Risk
Mm-hmm.
that something can explode somewhere. Do you agree? So if you
Yes,
operate
sir.
at lower temperature, you are playing safe. So contact process. Why do we use A2 ATM? Cost, safety reasons. Am I right?
Mm-hmm.
Safety reason. Cost, safety reason. Is that okay? I think that makes sense. So let's go.
Yes.
We are done with the contact process. Now, next one. Can you read? Can you begin to read? Bronsted is a person. Larry is a person. So we are going now.
Uh, it's not showing me where I'm supposed to read. It's still stuck on contact process.
What can you see now? What can you see?
Common acids.
Yeah, it's from Bronsted Lowry theory of acid and bases.
Mm-hmm.
We have
Sulfuric
common
acid.
acid. We have sulfuric acid. We
Mm-hmm.
have sulfurous acid. Look at the difference between them. Look at their names. So when it is for sulfuric, sulfurous,
Okay.
nitric, nitrous. Can you see now? The
Mm-hmm.
one that has more oxygen is the ake. The one that has lower oxygen is the us. We have not done oxidation state. Don't worry, we'll do it very soon. Sulfur here is +6. Sulfur here is +4. Nitrogen here is +5. Here is +3. Phosphorus +5, +3. Is that okay? So the one that
Mm-hmm.
has higher oxidation state or that contains more oxygen is the eke. Sulfuric, sulfurous, are you there?
Yes, sir.
Nitric, nitrous. Is it following a pattern?
Mm-hmm.
Is it following a pattern? Higher oxygen, sulfuric, lower oxygen,
Mm-hmm.
sulfurous.
Fine.
Higher oxygen, nitric, lower one, nitrous. Higher oxygen, phosphoric, lower one, phosphorus. Is that okay? Then
Yes.
hydrochloric acid. You have to know this acid. Which one sound new? The one that looks new to you. Which one among them?
Uh, Nitrous is the
Okay.
one that's new.
And maybe and sulfurous and phosphorus. Have you seen this guy before? Have you heard of it before? In
Phosphoric
GCS,
acid, yes. Yes.
when you react what 18 with steam, am I right? To get
Mm-hmm.
ethanol, hydration of 18 to get ethanol. This was the catalyst used. Do you get the point? Now
Okay.
your GCSE. So it's phosphoric
Mm-hmm.
acid. It's okay. Then this have you seen this guy before?
Mm, the carboxylic acids, yeah.
How many carbon? What's the name now? Ethanoic acid, two carbon in organic chemistry. One carbon is
Mm,
methanoic acid. Two carbon is ethanoic acid. What about three carbon? Met, one carbon, methanoic
oh,
acid. Earth, two carbon, ethanoic acid. Prop, three carbon, propanoic acid. Bute, four carbon, butanoic acid. Can you see now?
yes.
Are you there now? They are all
Yes.
carboxylic acid. All of them are weak acid. All of them are what? They are all weak
Yes.
acid. Is that okay? Methanoic
Yes.
acid, ethanoic acid, propanoic acid, and butanoic acid. They are all weak acid. You have to know these common acid. Is that okay? Then common alkali. Can you read
Yes.
them? Have you know? You are going. Tell me their
Common
names.
alkali. Lithium hydroxide, sodium
Correct.
hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide, and ammonia.
In case I'm with that. How do you know the formula of those hydroxide? Alkalis. Hydroxides is OH minus. So lithium group 1, sodium group 1, potassium group 1. Then magnesium group 2, calcium group 2, barium group 2. So this guy they have valency of 1. So what will be the formula? So all this guy, what will be the formula of the hydroxide? I can just say all this guy, I can just say they are MOH into 2. Am I right? Where M
Mm-hmm.
equals to what? Group 2. Do you get?
Yes.
Good. What about these ones? Is XOH, where X equals to what? Group 1. Do you agree?
Mm-hmm.
So ratio 1 to 1. So that's why we got this formula. So is that okay? So
Yes,
how do
sir.
we define an acid? According to Brunstellari, why do we call ammonia alkali? Why is ammonia called an alkali? Ammonia, why alkali? Ammonia, why it is it called an alkali? An alkali must contain OH that is soluble in water. That's alkali. Alkali is
Mm-hmm.
a soluble hydroxide, which is basic. Is that okay? Soluble
Mm-hmm.
basic hydroxide. Now, ammonia dissolved in water will form ammonium ion and hydroxide. Can you see it produces hydroxide? So ammonia in water produces hydroxide ion. So it is called an alkali. Are you getting it now? So
Yes, sir.
according to Brunstellari, what's an acid? I think you learned it from IGCSE, am I right? An acid
Yes.
is a proton donor. A base is a what? Proton acceptor,
At
right?
protein acceptor. Mm.
Yeah, go on reading.
I was saying it's a protein acceptor, a base.
Then go on, read on.
I'm reading which part, sir?
The one I mark now, this one.
Strong
Yeah, go on.
acids and bases are fully dissociated in solution. Weak acids and bases are partially, incompletely dissolved in solution.
So this,
Dissociated in solution.
thank you. So this guy, look at them. HCl, HNO3, H2SO4, they are all strong acid. Do you agree?
Mm-hmm.
Why? How do we, from the equation, what can you say from the equation that will show that they undergo complete dissociation? What can you say from the equation to prove that they undergo complete equation? What can you say? Tamuda, are you there?
Yes, sir.
The arrow is not reversible. The arrow is one way. That means it is complete. The arrow is one way. It's not reversible. Is that okay? The arrow is one way. One way.
Okay.
Can you sit down? When the arrow is one way, it is not reversible. Is that okay? That means it's a
Mm,
complete dissociation. When the arrow is two ways, look at this. Ethanoic acid going forward, going backward.
mm,
Cyanide going forward, going backward. Nitrous acid going forward, going backward. They are all weak acid. Weak acid undergoes incomplete dissociation. Strong acid undergo complete dissociation. Do you understand that?
yes, sir.
Thank you. There's strong alkali. Look at it. Sodium hydroxide. Can you see sodium hydroxide?
Sorry?
Can you see the mark I just made now? Can you see my sodium hydroxide? Are you there? Now that I'm talking
Okay,
about.
yeah, now
So
yeah.
NaOH is can you see now? One way.
Mm,
Strong. One way. Strong. One way. But this guy, two ways. Weak.
mm,
If it goes forth and back, it's weak. If it goes one way, it is strong. Is that okay?
yes,
Now, when a base, you say a base is a proton acceptor, right?
yes.
When a base accepts a proton, what does it become? Becomes a conjugate acid. We call it conjugate acid. Let me write it there for you. Good, thank God. This is a base. It forms a conjugate acid. Conjugate acid. When a base accepts a proton, it forms a conjugate acid. When an
Mm-hmm.
acid loses a proton, it forms a conjugate base.
Mm,
So this is base forms a conjugate acid, acid forms a conjugate base. When a base accepts a proton, it forms a conjugate acid. When an
mm-hmm.
acid loses a proton, it forms a conjugate base. Do you understand that?
Mm-hmm.
Good, that's fine. I'm going back to my notes. Can you see my note now?
Mm, where is it's on the equation still.
What can you see pH scale?
Yeah, pH
Yeah,
scale.
that's the note. So yeah. Can you repeat what's pH scale? pH
pH.
measures how acidic or how basic a solution is. Is that okay?
Mm,
What's the pH of neutral solution? Like water,
7.
7.
Mm,
pH above 7 is a basic or alkaline. pH below
mm,
7 is what? Acidic. Which pH is strongly acidic? pH of 0, 1, and 2. Strongly
mm,
alkaline or strongly basic? 12, 13, and 14. Am I right?
yes.
So what magnesium hydroxide is a weak alkaline. Suggest a value for its pH. Magnesium hydroxide is a weak alkaline. Suggest a value for its pH.
I'd say 10.
Magnesium hydroxide is a weak alkaline. A weak alkaline. Suggest a value for its pH.
I'm saying okay, 8.
9, 10, 11. But
Mm,
12, 13, 14 is a strong alkaline now. Am I right?
yes.
So from 8 to 11 is a weak alkaline. 12 to 14, strong alkaline. 6 to 3, weak acid. 2 to 0, strong acid. Do you get the point now?
Yes.
And 7 is now neutral. Is that okay?
Mm.
Thank you. How do we measure pH?
Use of a pH meter, use
Stop
of
there,
a
stop there, stop
universal
there. Stop. Let me show you that what that means.
pH meters. Oh, I
Thank you.
saw one of these during our chemistry class.
So you should measure pH directly. You should measure. So chemistry
Mm.
should remember method of is in your. They just add it to your snapboard. How to measure pH of number one? What can you use? pH meter. Is that okay? Number
Yes.
two, what can you use also?
Universal indicator.
Have you used that before?
Yes, we have.
Okay, let's look at it again. Can you see? So what's the color of universal indicator in very strongly acidic solution?
That's red.
Red. In very strong alkaline solution, purple.
Purple.
Though Cambridge marks both purple and blue. Is it mark both purple and blue? But strong alkaline is actually purple. Strong acid is red. What about weak acid? Orange or yellow? Is that okay? Weak acid. Are you there?
Yes.
Orange. What about
Green.
neutral?
Neutral is green.
And strong weak base, blue. Is that okay?
Blue.
You have to remember those colors in your GCSE. You can actually level also.
Okay.
You have to remember those colors. Let me just a kind of summary. Good. So universal indicator. Universal indicator color chart. pH 1012 red, 2, 3, 4, 5, 6
Orange.
orange or yellow. Then 7 green,
Green.
8 to 11
Blue.
blue, 12 to 14 purple.
Purple.
So that's you remember that. So you remember that. Now let's go back to our class again. So you can use number 3. You can use what?
Conductivity
Conductivity
method.
measure. What that means is that strong acid is a better electrolyte. We conduct better than weak acid. If you do this now, if you go and do this, maybe
Mm.
you carry out electrochemistry, electrochemical cell, connect them. You now put strong acid also. Connect them together. Then connect them to what? To an external bulb here. If the acid used as strong acid, the bulb will be very, very, very bright. Is that okay? If it's a weak acid, it will be very, very dim. Is that okay? These
Yes.
are measuring pH, conductivity method. What that means is that strong electrolyte or strong acid and strong alkaline, they are better electrical conductor and they have high conductivity. Is that okay?
Mm.
Are you there? That's good.
Yes, sir.
Now, is that your next one? Go on.
Neutralization reaction. It occurs between hydrogen,
Proton
proton
from an acid. Yeah, H
from
plus is proton.
acid and
Is that you say
hydroxide.
hydrogen ion or proton, not hydrogen? That is called hydrogen ion or proton. Yeah, it's occur between what H plus from an acid and OH plus from an alkali to form what water. So these are examples of neutralization reaction. You said you know what it means in your syllabus. All the note I form business syllabus. HCl and KOH, KCl and water. Nitric acid and sodium hydroxide, sodium nitrate and water. Ethanic acid and lithium hydroxide. Lithium ethanoate and water. Sulfuric acid and potassium hydroxide, potassium sulfate and water. All these are what? Examples of what? Neutralization reaction. Yeah, go on. What do I write? Can you read?
Ironically, neutralization reaction can be represented as
H plus OH minus to give water. That's how to represent all of them. There's
mhm,
H plus from acid. There's OH minus from water and it from water. Is you get the point now? It
yes.
produces what? Salt and water only. Is that okay? Now,
Mhm.
nitrogen cups. So now, what do I skip in what did I skip anything in what I've taught you so far? I said I would let me
No,
just
A lot, and you're like, okay, do you have a private tuition? Don't you have? Do you have? And yes, Agile Tech do have a private tuition. So by my right, you can see that we have for the EdExcel and Cambridge IGCSE. And yes, we do have for all subjects. Okay, all subjects. Okay, the popular ones that's always been in demand is mathematics, English language as a second language. Okay, we have physics, we have biology, we have chemistry, and we have um, you know the flagship, which is ICT, just here and there. We also have business studies. So if you're interested for a private tuition, um, I think all you have to do is send an email to the sales team at agiletech@gmail.com, and they would reply to you, talk about your time zone, talk about and the fees really quite affordable. Really, it's really quite affordable. It's when you look at it across um, other tutoring service, I think this is the one that's quite affordable and you get the very best of service. We also have for the E levels as well, um, and also for the edXL. So we have for the Cambridge E levels and edXL E levels. Okay, and we have also across the subject mathematics, which is usually the hot cake when it comes to E level mathematics and chemistry, and then biology. These are usually one of the ones we have in demand always, all the time, even physics, for E level. So all you have to do, if you're watching this right now and you are interested for a private tuition, then you can do yourself a solid, okay, and send an email to the sales team at Ajiro at gmail.com and they'll reply to you. And the good news about this is what I've discussed with the sales team is we've tried as much as possible to see how we can subsidize the amount according to countries, so it doesn't really look very, very heavy. Okay, so this is really important. Yes, we do charge in pounds, but again, we try to be as much as possible considerate to your countries, and we don't just skyrocket the price. No, because at the end of the day, we know how it feels, and we really want you to actually get the best of service, and again, be able to afford it from the comfort of your home. So again, Agile Tech private tuition is currently ongoing. You can enroll yourself for the IGCSE and then for the E levels. Again, for the IGCSEs, these are the subjects, and for the E levels, these are also the subjects. So, again, what are you waiting for? Just send an email to the system. If you're an IGCSE student preparing for IGCSE, if you're watching this in 2025, watching this in 2026, watching this in 2027, we're currently ongoing, and this is actually a good time for you to actually explore and then get it tailored to your own needs. So trust me, you don't want to miss out.
Under chemical bonding, did I skip anything? Under chemical bonding.
Chemical bonding. Yeah, there's a part you skipped, hybridization.
Hey, I'm skipping. Can you note it down? I write it down now, so I'm not teaching now. It wastes my time.
Okay. All right.
Write down hybridization. Write it down.
Mm-hmm.
No, remind me. Oh, write somewhere you know
Okay.
you remember. Hybridization and titration of curves. Write it down. I'm skipping it.
Okay.
So
I've
that's the end of
written.
this topic. I'm skipping it. It waste my time.